Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE, and BIT SAT. He has more than 16 years' experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth, and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series on oscillations and waves. In this lecture, we are going to learn about the vibration happening on stretched strings, the different modes possible in the stretched string, followed by the musical notes and about tuning fork. All these concepts we are going to learn in this lecture. Let us see the session outline before we start the lecture. In this lecture, we are going to learn normal modes of vibration in strings, overtones and harmonics, then about musical notes, the theory of tuning fork, followed by Melde's string experiment. We will start our lecture with the concept of vibration that is happening in stretched strings. We have the knowledge about the velocity of the wave that is propagating in a stretched string. With that, we will start today's lecture. When vibrations are set on a stretched string, standing wave pattern is formed. The vibrating segment is kept between two supporting ends. They are called knife edges. Sharp edges will support the vibrating segment, and reflection that is happening at the knife edge, there is a standing wave pattern formed on the string due to the superposition of the two waves travelling forward and in the return direction. So, let us start our discussion with the vibration that is set on a stretched string. In stretched strings, when vibrations are set by plucking it, standing waves are formed in it. This is because the waves are reflected back by knife edges kept at the ends. This makes the reflection from rarer to denser medium type, which will result in phase change of pi. Eventually, nodes are formed at the ends. This makes loop-like appearance in the vibrating string. These loops are formed by the nodes and antinodes, which are alternatively formed on the stretched string. So, let us see how the string, when it is vibrating, will look like. The vibration that is happening on the stretched string will look like this. The left hand side picture shows the static case, the photographic picture. The right hand side shows the dynamic case, the vibrations are happening. Here, in the first case, there is only one loop formed. This one loop is of the wavelength, and the second case, two loops are formed, and in the third one, three loops are formed. In the second loop, the wavelength is equal to the length of the vibrating segment, and in the third case, the length is equal to 2/3 of the vibrating the wavelength, and this kind of wave pattern is formed in the string. But we should have noticed one important feature: at the ends only the nodes are formed. That is the typical mechanism happening due to the reflection at the knife edge, which is a denser part or denser medium. Now, with this idea, we come to a conclusion that the vibrating segment will have loops formed in it. And what will decide the number of loops? What factor or what character of the vibration decides the number of loops? Is it going to be one loop or two loop, many loops? Which will decide that? We need to learn the concepts further to get an answer for this. So, let us proceed to find out an answer. On what does the number of loops depend? For this, we need to take the basic equation for velocity of wave in stretched vibrating string. This equation is a already known equation. The velocity of the wave that is set on the string is equal to square root of tension in the string divided by the mass per unit length of the string. So, this is a known equation for us. And what is the inference we get from this? There are two other equations we should keep in mind. The velocity is proportional to square root of the tension in the string, and also the velocity is inversely proportional to the square root of mass per unit length of the string. These are the characteristics of the medium, the string. And where does the number come? The number of loops. We need to modify this basic equation to get an idea about the number of loops that is going to be formed on the vibrating segment of the stretched string. So, let us try to modify this equation so that we get some idea about the number of loops formed. Let us proceed further. The velocity equation could be rewritten for frequency as follows. So, we have started with the velocity equation just we had seen before, and velocity is the product of frequency and wavelength. So, we substitute for the velocity with the product frequency and wavelength. We are interested to retain the frequency on the left hand side. So, the lambda is brought to the right hand side in the denominator, and this lambda has got a direct relation with the length of the vibrating segment. So, this equation gives us the idea. In the first case, the length is equal to half the wavelength, which is denoted as lambda 1 divided by 2. In the second case, the length of the vibrating segment is equal to a full lambda, but this lambda is not equal to the lambda 1. So, we are showing it with the suffix 2, lambda 2 it is a different lambda. Third case, it is 1 and half or 3 divided by 2 times the lambda 3, because 3 loops will be formed. So, if you look at this equation, this terms, here 1 lambda is there, second case it is 2 divided by 2, so that is 2, 3, and here it is 2 divided by 4, so that 2 comes. So, like that 1, 2, 3, 4, 5 and so on, they appear in the sequence, and finally we write n times lambda divided by 2, and here this lambda is different. So, we denote it as lambda n. So, when we incorporate this final general term into the equation, we finally get the frequency of vibration is equal to n divided by 2L square root of T divided by m, and here this n comes, this n tells the number of loops formed in the vibrating string. So, what is the conclusion? What decides the number of loops formed on the string? It is the frequency with which the vibration occurs. The frequency indeed depends on the velocity. The velocity indeed depends on the tension in the string and mass per unit length of the string. So, this is how the n appears in the expression. So, finally, we arrive at a conclusion: the tension and mass per unit length, they decide the frequency and thus the number of loops formed in the stretched string. What next we have? We need to find out some basic concept, so that how the frequency is going to vary sequentially with 1 loop, 2 loop, 3 loops and so on. That will make our case easy to come to a conclusion: what is the frequency of vibration happening with the number of loops formed. So, only by measuring the number of loops we will be able to come to a conclusion for the frequency of vibration. We are moving towards that by modifying the equations further. So, let us go ahead with the learning. The possible modes of vibrations are sequentially discussed here. The first one is fundamental frequency, because with that only the vibrations start. In the first vibration, the transverse stationary wave is formed in the wire of length L with one loop between the ends. So, it is taken as the first ever frequency, it is denoted as F1, and we have the terms having the same meaning. This frequency is also called fundamental frequency as it is produced by the first vibration. The first vibration is called the fundamental frequency, which is denoted as F1 here. Now, what is the next mode of vibration? Let us look at the diagram and understand it. In the next vibration, two loops will be formed in the wire of same length. So, which is denoted as the frequency F2, the number of loops is 2, the remaining terms are the same. So, we are able to find out this F2 is 2 times F1. This F2 frequency is called the first overtone as it is produced first time over the fundamental frequency. So, we need to know the meaning of the technical terms we use here. When we say the first overtone, it is over the fundamental first time occurring. So, it is called first overtone. The beginning is from the fundamental. Next to fundamental, it is first overtone. We should not be carried away by the word first used in the first overtone. The first overtone occurs in the two loop case that comes next to the fundamental, but still called as first overtone. Any other terminology is used to specify the frequency. This is how it is specified. This is also called the second harmonic. The meaning of second harmonic is 2 times the fundamental frequency. See, it is appearing twice the fundamental. F1 is fundamental. So, the first overtone is the second harmonics of the vibration. If we take up one more case, we will be able to arrive at a general conclusion. Shall we take the next possible vibration also? Have a look at the slide. The second overtone, if you take, in the next vibration 3 loops will be formed in the wire of same length, and accordingly the equation is modified. Now, it is altogether a different frequency F3. This 3 comes because of the number of loops, and we are able to identify this F3 is 3 times F1. F1 is the fundamental. This frequency is called the second overtone as it is produced second time over the fundamental frequency, and this is the frequency 3 times that of fundamental. So, it is called the third harmonic, and it goes on and on and on as the number of loops increases. And what is the conclusion we arrive at? What is the relation between the overtone and harmonic frequencies? Let us generalize the relation between the two as far as a stretched wire is concerned or stretched string is concerned. This is the conclusion. Hence, for higher overtones and harmonics, we can generalize for a vibration in stretched strings as the nth overtone will be equal to n plus 1th harmonic. This is one way of representing it, or we can represent it the other way also. Nth harmonic will be equal to n minus 1th overtone. Any one we can keep in mind. I think the first way of representing is somewhat easy for us. The nth overtone is n plus 1th harmonic. This one standard equation we can keep in mind as far as the vibrations in stretched strings are concerned. This forms the basis for the musical notes in string instruments. This concept of overtones and harmonics are the basics for the musical notes that are developed in stretched strings, which are used in string instruments. What are the string instruments? Immediately come to our mind definitely guitar, violin and related instruments come to our mind. Shall we see the science behind these musical instruments which use stretched strings for producing sound? Shall we have a look at it? These are the examples of string instruments. In these string instruments, different strings are kept between the fixed and one adjustable end. In the adjustable end, we have the screws which could tighten the string, and shall we have a closer look at it? So, this is how it is done. The screws are used to vary the tension in the vibrating strings, and look at the thickness of each string. The top one is a very thin string, the next one has got slightly greater thickness and the thickness keeps increasing. The extreme down has got a larger thickness, and that obviously will vary the mass per unit length of the string. So, the two factors are adjusted, the tension in the string and mass per unit length of the string are adjusted. And what about the length of the vibrating string? That also plays a role. Can it be varied? Have a look at the picture once again. Here we have different knife edge kind of arrangement. Actually, in the typical arrangement, the strings will not touch the support. When we press these strings between the two knife edge arrangement, this gap is called fret. In guitar it is called fret. So, when we press, the contact is closed here. So, this becomes the vibrating length. So, all three factors could be varied in this kind of instruments. The tension in the string, the mass per unit length, that is different string is used, and the length of the vibrating string also could be varied. What do we generate out of it? Different frequencies, and here comes the music of science, the physics behind music. Shall we have a small part of the musical notes for our understanding? Shall we see what are the musical notes that are developed for generating the different musical sounds? We will have a look at it. The fundamental musical notes are shown here. There are 7 swaram. They are called swaras in Carnatic music: sa, ri, ga, ma, pa, da, ni, and the sa again comes as the 8th one. In Western notes, they are called C, D, E, F, G, A, B, and again the C repeats. So, 7 notes are there. The 8th one is called the octave. It is called the next octave starts with the 8th one and it goes on. And what about their frequencies? One typical set is shown here: the 256, 288, 320, 341.3, 384, 426.7 and 480 hertz respectively for each note starting from C up to B. And this is how the sound is produced, and each will have a different frequency, and this values I have shown here is for one octave. Like that, several octaves will come. The professional keyboard will have around 7 octaves, 7 different such sets will exist. All these notes combine together to give chords. They call it as chords in musics. So, the basic of music starts from the science, and the science explains how the musical notes are formed. Now, we will go ahead and learn the further concepts about the sound that is produced using different instruments. The basic instrument as far as science is concerned which could produce sound is a tuning fork. You might have learnt about the tuning fork in the school subject. In lower class itself we would have learnt it. But what is the concept or the science behind a tuning fork? Shall we learn about it? The principle of tuning fork. Tuning fork is a 2-pronged steel device used by musicians which vibrates when stuck to give a note of specific pitch. Here the meaning of pitch is a specific frequency, we can say. This is showing a typical segment of stretched string or a material. The vibrations are shown here. Here, contrary to the stretched string, in stretched string what is kept fixed? The two ends are kept fixed as far as a stretched string is concerned. The ends are fixed between the knife edges, but in this case the ends are free to move, vibrate. The central part is fixed, and if it is bent, we have this kind of structure. And finally modified one is called the tuning fork, which is fixed here, and here we have the handle. When we strike this end, we will have the vibration produced in the prong, and this will produce a specific frequency. So, this is the science behind the tuning fork. This produces a musical note. I would like to give a small demonstration how different frequencies would appear. Before I could give a demonstration, we will have a look at a picture that will give a greater understanding how the tuning fork will look like with the frequencies written or engraved on them. See, this is a typical picture which shows different tuning forks with different frequencies written on them. The C note is 256 and so on. All these are printed on a tuning fork. It ends with the octave C, the next octave 512 frequency. And if you have a careful look at the tuning fork, they differ in the length. So, this length will vary the frequency. I would like to now show a demonstration of the frequency produced by the tuning fork. Shall we listen to the sound produced by the tuning fork? Listen to it. This is one frequency. This frequency is the 512 frequency. Next, another tuning fork with a slightly greater length. This has got another frequency. It is printed as 480 hertz. And what about still lower frequency? The length is greater than the previous two. It is 341 hertz. I hope you would have listened to different frequencies formed by the different tuning forks. Because the length of the vibrating segment is different, we have different frequencies when they vibrate. Now, is this tuning fork having a direct application in any of the experiments? We have one experiment called Melde's string experiment, in which the tuning fork is used for finding the frequency with which a wire is vibrating. Actually, in a typical Melde string apparatus, we are using the apparatus to determine the frequency of a vibrating tuning fork or a vibrator which is normally made to vibrate by electrical means. An electromagnet used to set the tuning fork in vibration, which is connected to a battery. There is a contact maker marked as CM in the diagram, whose position can be adjusted for setting the tuning fork to vibrate. As current is passed through the electromagnet, the prongs are attracted inwards. Thus, the contact is broken and the current is stopped. Now, the prongs return back to make the contact, thus the vibration continues. A string attached to one of the prongs of the tuning fork or the free end of the vibrator carries the same vibration. This explains about the apparatus called Melde's string apparatus. How it looks like, have the visual here. This is the tuning fork which is made to vibrate with the help of an electromagnet, and here we have the contact maker. This contact maker is always in touch with the prong, any one of the prongs of the tuning fork. Actually, the tuning fork is not mechanically made to vibrate, it is remaining stationary, and when we switch on the circuit, the current passes through the electromagnet. The electromagnet attracts the two prongs towards it, and thus the contact is broken. Once the contact is broken, current is cut off. Once again the prongs will come back, make contact, again it will get magnetized. So, this vibration continues in the circuit. It is a very elementary. At what frequency the tuning fork will vibrate? The tuning fork vibrates according to its frequency with which it is able to vibrate, and what enhances the vibration? It is done by the electromagnet. It will not vibrate at the AC frequency. We should not have that misconception. It is operated by a battery which gives direct current. Once again have a look at the picture. It is operated with the direct current. So, the vibration is decided only by the tuning fork. The frequency is decided only by the tuning fork, and we are interested to find out with what frequency the tuning fork is vibrating. We sometimes need not use a typical tuning fork. We can have one single vibrating segment between the electromagnets. So, in that case one single vibrator will vibrate to and fro, and we are interested to find out with what frequency the vibration is happening. To measure it, we can attach a string to the vibrating segment, and we can make the loops formed on the vibrating segment, and we can typically calculate the frequency, and that will be the frequency of the vibrating segment. So, it is an indirect way of finding the frequency of the vibrating tuning fork. How it is done? Let us see the concepts further. Now, there are two ways to make the string vibrate by keeping the position of the string with respect to the vibrating tuning fork or vibrator, which is called transverse vibration mode, and next one is longitudinal vibration mode. In transverse vibration mode, the prongs are moving up and down, the string is kept perpendicular to it. In longitudinal vibration mode, the vibration is happening in the direction in which the string is kept. So, the pictures are self explanatory. We have masses attached to the string so that the tension could be provided for the vibrating segment. How to find out the frequency in the two cases? In the transverse mode, the key point is the time during which the tuning fork completes one vibration, the string also completes one vibration. So, the typical formula can be used. When the string vibrates along with the vibrating segment. In the longitudinal mode, the time during which the tuning fork completes one vibration, the string completes only half of the vibration. So, the formula is to be modified, the 2 is dropped in the formula. So, by these two methods, the frequency of the vibrating string could be identified. Hope you would have understood the concepts related to the tuning fork, musical notes and all. Now, it is time for us to go for summary. In this session, we have seen the concepts of normal modes of vibration in strings, overtones and harmonics, musical notes, theory of tuning fork, Melde string experiment. Before we wind up, we will test our understanding by answering these questions. Explain the vibration modes in stretched strings. What are overtones and harmonics? Give the relation between overtones and harmonics for vibrating string. Discuss the signs of musical notes. What is a tuning fork? Explain the Melde string experiment. With this, I would like to wind up today's lecture. Thank you for watching the program.